So, future trends. As you can imagine, it's not actual technology, right? It's a mindset, it's an attitude, it is an approach. At Syska, one of our approaches is to really integrate everything together. You know, one of the biggest issues in the energy marketplace right now is the duck curve. California's had a massive problem with the duck curve. The duck curve is rearing its head in Texas, and it'll be everywhere else relatively soon. What the duck curve is, in simplest terms, is that renewable energy is going to produce huge amounts during lunchtime hours, and then in the kind of 3 o'clock to 7 o'clock in the afternoon, the solar has gone down, the wind hasn't quite picked up yet, and yet that's when our buildings need the most energy. So we have this 3 to 4 hour period where we have this massive demand, and right now it's falling on our fossil fuels. And we have an opportunity. Generally, people look at addressing the electrical demand problem with electrical energy solutions. It doesn't have to be that way, right? So much of the demand at that point is actually cooling. So we're looking at ways to use thermal energy storage at the building scale. So not every building has the opportunity but every building that has chilled water has the opportunity for thermal energy storage. And so we actually have the huge opportunity to attack one of the bigger problems that the grid has right now with our own projects through thermal energy storage. There's a lot of interest right now in sand and bricks and other ways of taking excess solar energy and then turning it into basically like 1,000-degree temperatures, putting it into these bricks or sand and storing it for 6 months before you actually then tap into it. I think the biggest thing that we are kind of keeping our eye on is how we're going to incorporate hydrogen into our buildings, right? Everyone's been talking about the hydrogen economy for 15 years, 20 years? You know, hydrogen fuel cell cars were supposed to be the next thing, but then the battery technology kind of beat it out, right? We're seeing the same thing in the buildings. Like, we have these opportunities.
The things that Chris mentioned, they're not new. Thermal energy storage, bricks and sand, these are not new technologies. And that's kind of the point. We have the technology to meet a net zero society, energy demand, building design. It's the act of applying those technologies and understanding them. You asked about, future trends. The future trend is applying the things we already know and making it work for us and using less energy, not being wasteful about it. That is really important, and that is the future. We have to think about not just the energy use of our systems, but the embodied carbon of those systems. And embodied carbon, normally, if you think, the first thing that comes to mind is concrete or glass or steel. Now we're taking that a step further. What is the embodied carbon of the mechanical systems that go into our buildings that keep us comfortable? What is the impact of refrigerants and the fugitive emissions related to refrigerants as they leak? Because they leak. The manufacturer will say 3%, 5% a year. Well, that's actually a lot. And then that's only from day one. Once you're talking, you look 15 years in the future, the equipment has a 20 or 25 year lifespan. So you're 3/4 of the way through its life. Now it's at 30% leakage. That's a lot of refrigerant escaping that, first of all, is a health hazard. The second of all, could contribute just as much emissions as the operational emissions of your building, which we're now realizing. So in terms of technology, there's so much we already have. There's still some we're left to figure out, but it's piecing all those things together in an intelligent manner.
And that's actually what kind of Syska's thermal network loop is all about. What we're trying to do is really integrate all the different building systems. It's able to collect heat where the heat's being generated and provide heat to where the heat is needed. We have been including heat recovery chillers into healthcare projects for quite some time. We have a simultaneous heating and cooling load. Healthcare is big on that, and that it just makes sense. However, almost all of our buildings, you look out through here, and all of these buildings in the middle of the winter, it's 0 degrees in New York City, right? On a daily basis, they are still producing more heat than they need, or even, more importantly, at times that we don't need. So what we've been looking at it was kind of this like 3-step process, if you will. First is for simultaneous heating and cooling, we just do the heat recovery chiller concepts. Second, for daily balance, we use the thermal energy storage. So what we end up doing is we're making chilled water in the morning when we need to produce heat in the space. And then we melt that chilled water in the afternoon when we have excess heat. So that whenever we're looking at those daily swings, we really tap into thermal energy storage concepts. The next level is the seasonal, and that's really tapping into the ground, where we're collecting heat in the summer, using it in the winter. Just really looking at each of our projects and our opportunities from that lens allows us to really figure out how to get the most out of the thermal network.
Chris likes to think of it in terms of leveraging the fourth dimension, which I like, because that fourth dimension being time is really important. In one moment in time, you may just be in cooling mode, but in 6 hours, maybe you'll be in heating. And so using time and using thermal storage or other forms of storage, battery storage, to your advantage will help with load management, with grid harmonization, with keeping people happy and comfortable, but also reducing our emissions and our utility bills.
Yeah. I mean, out in Los Angeles Federal Courthouse, about half the heat each kind of for our peak day was happening during morning warm-up. When the building's at 55 and you need to warm that whole mass up, we need to dump some heat into it. So where does our heat recovery chiller get its heat from? People aren't there yet. The building isn't producing the heat that we need. We recognize that we add 1,200 tons of pipes of condenser wire going from the basement to the roof, right? Well, all night long, all of the data equipment is just kept warming up that water. We didn't reject that heat. We just allowed the data room, the server rooms, all the IDF closets, the back of house transformer rooms, all of that to just heat up all this water. And then on Monday morning, when the building needed all that heat, we actually had, I don't know how many hundreds of thousands of gallons are in that tank, but we had a lot of water. All it was a control. We did nothing different besides just not reject all that heat all weekend long or all evening long. We just held on to it and used it later. That concept started at that one condenser water loop at LA Fed.
That's the cool thing about this concept of the thermal network loop, because you're combining systems that, for the most part, we usually disconnect. Most of our equipment, the IDF and data center cooling, the space heating and cooling, they're all different pieces of equipment that don't talk to each other.
Yep.
And a lot of times they're operating in different directions at the same time. So you got some things in cooling, some things in heating, and they don't talk. The things in cooling are rejecting heat to the atmosphere. The things in heating are, they're doing their thing. The thermal network loop is our way of connecting those dots and connecting those pieces of equipment to scavenge heat, recover heat, and put heat where it's needed instead of having to generate and regenerate. So the data center can be connected to domestic hot water, and we don't have to have compressors running in different directions at the same time.